Okay, let's take a look at some examples of finding derivatives of functions using those rules that we've just taken a look at. So our first example here, we've got the function y equals x to the power of 8 minus x to the power of negative 8. And we want to find the derivative of it. So our derivative, dy dx, okay, we can use the sum and difference rules here. So the difference rule tells us that we can treat this function as this function minus this function. So we take the derivative of our first function and then subtract the derivative of our second function. So the derivative of x to the power of 8, we just use the power rule. Bring down the 8, keep the x. 8 minus 1 gives us an exponent of 7. So the derivative there is 8 times x to the power of 7. Then we're going to subtract the derivative of our second term. So the derivative of our second term, we're going to bring down the negative 8 as an exponent, keep the x, and then negative 8 minus 1 is negative 9. So our derivative function is going to be 8x to the 7 plus 8x to the negative 9. And if we're dealing with negative exponents, remember we can always rewrite negative exponents by moving that term down into the denominator here. So this could be written as 8 over x to the power of 9. Let's take a look at our next example here. F at x equals x plus 3 squared. What should we do with this one here? Well, I think this is a case where we want to rewrite the function before we take the derivative. So we want to take our function, f at x, and we want to expand this out. So x minus 3 times x minus 3 gives us x squared minus 6x plus 9. So now we have a polynomial function. We've got addition between all the terms, so we can just do our derivative term by term by term. Now, the notation is important here. My original function is f at x, so when I'm rewriting it, I rewrite it as just f at x. When I go ahead and take the derivative, now I can say that I'm finding f primed at x. And it's only at this stage when I start to do the derivative that I put that prime in there. So our first term is x squared. Derivative of x squared, we're going to bring down the 2. We're going to have the x. 2 minus 1 just gives us 1. So we don't actually write the 1 there. But we can kind of imagine that there is an exponent of 1 there. Okay. Our next term, 6x. Well, like we just said, we can imagine that there is an exponent of 1 there. So when we do our derivative, we are going to bring down that 1. 1 times 6 is just going to give us 6. And we're going to be left with x to the exponent 1 minus 1 is just going to be 0. But anything to the exponent 0 is just 1. So this is essentially just going to go away and become 1. Then our last term, 9, well, 9 is a constant, so the derivative of a constant is just 0. So it would be like having a plus 0 there on the end. So we can clean this up a little bit. 2x plus 6 is our derivative, because we never write the plus 0 terms or anything or things like that. Our next example here, y equals 6 over x cubed plus 2 over x squared minus 3. This is another case where we're going to want to rewrite the function before we take the derivative here. So I'm going to rewrite this. 6 is going to be my coefficient, but I know if I have x to the power of 3 down in the denominator, I can write that as x to the negative 3. Next term, 2, x to the negative 2 in the denominator, I can write that as x to the negative 2. And then my minus 3 stays as a minus 3. So at this stage, if you've got a confusing function, sometimes it's best to try to write it as close to in form as a polynomial. So this looks a lot like a polynomial here. We've got 6x to the negative 3, and it makes it really easy to apply that power rule. So let's take our derivative. Y primed is going to be, we bring down the negative 3. Negative 3 times 6 is negative 18x, and then if we subtract 1 from the negative 3, negative 4, plus, we're going to have negative 2 times 2, so that's going to be negative 4x. Negative 2 minus 1 gives me negative 3. And the negative 3 term, well, it's a constant, so it's just going to be 0. So now I can rewrite this. I'll have negative 18. I can take that x to the negative 4 and put it down in the denominator as x to the power of 4. Positive and negative give me a negative, so I'm going to subtract 4 over x to the power of 3. Again, taking that negative exponent and writing it as a positive exponent down in my denominator. Our next example here, f at x equals root x plus 6 root x cubed plus root 2. So again, we want to rewrite our function, making it clear what the exponents are. So square root of x, well, if we're taking the square root, that's equivalent to having an exponent of 1/2 on x. 6 is going to be our coefficient. If we've got the square root of x cubed, the cubed gives us the numerator of our exponent. If it's square root, we're going to have a 2 down in the denominator of our exponent. And the root 2, we can just leave as root 2 because we know that root 2 is just a number or a constant, and we take the derivative of that, it's just going to go to 0. So let's go ahead, take our derivative here, bring down our exponent, 1/2 x to the power of 1/2 minus 1 is negative 1/2. And then our next term is going to be 6 times 3 over 2, bringing down the exponent, x to the, let's see, 3 over 2 minus 1 is 1/2, or 1 over 2. And now we can clean this up a bit. I'm going to bring the 1/2, I'm still going to have a 1 up in my numerator and a 2 down in my denominator, but I can take the x to the negative 1/2 and write it in the denominator as root x. For my next term, I've got, let's see, 6 times 3 is 18. 18 divided by 2 is 9, so I'm going to have a 9 as my coefficient, and then just root x here, changing that fractional exponent into a square root. Our last one here, we've got x squared times root x. I think this is another case where it's best to rewrite it here. So first step, keep the x squared, rewrite that x as x to the 1/2. Okay. Now we've got two terms multiplied together, and at the end of this unit we're going to look at the product rule that teaches us how to handle it when we've got a function times another function. But at this point right here, it's easiest just to simplify this. If I'm doing x to the power of 2 times x to the 1/2, I can just, if I'm multiplying powers of the same base, I can add the exponents. So I want to think of this as x to the power of 4 over 2 times x to the power of 1 over 2. I've got a common denominator, so I can add those exponents, x to the 3 over 2. Now notice at each step here, I've just said that I'm just rewriting my original function. So it's y equals, y equals, y equals, y equals. Now at this stage, I'm ready to take my derivative. So I can bring down that 3 over 2. I'm taking my derivative, y prime, 3 over 2 x to the 3 over 2 minus 1 is going to be 1 over 2. Oh, I should go back. I subtracted my exponents instead of adding them. Back we go. Erase, erase, erase. Okay, so at this stage right here, x to the 4 over 2 times x to the 1 over 2. Add the exponents and we get 5 over 2. Not sure why I subtracted them. Now we can take our derivative. 5 over 2, x to the 3 over 2. Or if I wanted to rewrite this to get rid of that fractional exponent, I could write this as 5 over 2. The 2 in the denominator gives me a square root, and then I can have an x cubed there.